Right, so let's begin. Today we are going to solve some problems from problem set number 2, which is about compression members. All right, so let's begin with question number 2. I'm skipping number 1 because you have to do some calculations, like you have to create Excel sheet, etc. So I'm skipping that to you. And if we go to question number 2, in here we have to compute the design compressive strength and allowable compressive strength for each of the following columns. Let me take a pointer. Okay. So we have two columns, as we can see in this problem. We have first part A. In part A, we have the column HEM 320 pinned from top and bottom, as we can see. No intermediate supports, and we're supposed to compute the compressive strength based on first the given steel S275 and based on the other kind of steel S355. So if we begin with part A of this problem, first of all, based on the, we have to find the member capacity in global buckling. Now, usually steel columns or the members in compression, when the material is steel, we don't really fear the failure in compression, but we fear the buckling. So that's why usually we get the capacity of a column from checking the local buckling, or sorry, the global buckling. So from here, this equation here, we can find the global buckling capacity or the compressive strength capacity for this column. And it is according to LR of D, since we are multiplying by 0.9. Here we have area gross multiplied by FCR. Now, in this problem, we have to find FCR in order to find the capacity. So how do we do that? First of all, you have to check for the slenderness. Now, we have to check whether KL over R is less than or equal to 4.71 multiplied by E square root of E divided by Fy. Now, if KL over R is bigger than or equal this part, FCR would be equal to 0.877 by Fe. But if KL over R is less than or equal this part, FCR would be in this case the other equation, as we can see here. Now, once, as you can see here, we have this term Fe. What is Fe? We can find it from this equation, from Euler's buckling, pi square multiplied by the modulus of elasticity divided by KL over R squared. So mainly we will be using these equations to find the capacity of a column in compression. Now to continue with this problem, okay, now as we can see here in this problem, we have the column in pin-pin condition. And first I will consider this material in here, S275. And since the column is pin-pin, we are actually going to consider K equal to 1. Now, why do I do that? Because from the AIC, if we take a look at the AIC in here, we can see that in the case where the column is pin-pinned, the theoretical value of K would be equal to 1. Now, going back to the problem, we have K. Now we find KL over R. But since the column would be buckling actually in one of the directions, either about the x-axis or the y-axis. So what do I mean by that? Now, since it's a wide flange, so either the column would be buckling about the x-axis or about the y-axis. That's why I have to check KL over Rx. And if I do that, 1 by 3.8 meters divided by Rx, which is taking from the sections table for HEM 320, and divided by 100 to convert from centimeters the Rx to meters, you get your KL over R initially 25.71. Now, if we check for the other direction about the y-axis, KL over Ry now becomes here we can see the y is reduced, and this value would become 47.8. So for KL over R, now I have two values, 25.71 and 47.8. which one am I supposed to proceed with? Well, you have to pick the biggest value. Why the biggest value? It's critical because if you have seen this figure before, here we have in the y-axis FCR, and the x-axis we have KL over R. As KL over R increases, the capacity of the member decreases. That's why 47 is located here and 25 is located here. So obviously, this one would be more critical. Now, we check for the slenderness of this member. KL over R, is it less than or equal or more? And in here, I'm plugging in the value 47.8, which is here, and comparing it with what I have on the right-hand side. So in here, we have 200,000 megapascal modulus of elasticity for the steel divided by the yielding capacity of the steel, 275, which is from here. And if I check this, I realize that the KL over R value is less than or equal to 127. So in that case, I'm going to use this equation for finding FCR. Now, before finding FCR, I need FE. So FE would be equal to pi square multiplied by 200,000 megapascal divided by KLR value squared. Now, in this case, I obtain FE would be equal to 863.92 megapascal. Now, notice something, this is in megapascal. Do not forget this unit, guys. Also, now, since I have FE, I can proceed to calculate FCR. So as we said before, from the slenderness, this is my equation in here. So if you plug in the values, 0.658 to the power of 275 divided by FE, multiplied by 275, you get your FCR equal to 240.7 megapascal. Now we can find the capacity of this member by multiplying by the gross area for HEM 320. And here I have the area gross multiplied by FCR and the reduction factor, or the factor of safety, according to LRFD. So from here, I get the capacity for this member in case I equal to 6,758 kilonewtons. Now, if you continue with this problem and check for case number 2 with different steel, you will be doing the same procedure again, but the only thing that will be different with you, Fy. Here, and all the procedure would be the same. Now, going to part B of the problem, number 2. In this part, we have, as we can see, IPN 450 pinned from top and bottom and braced at mid-height in the weak direction only. Compute the compressive capacity for this member. So if you actually consider this IPN 450 and sort of like draw a 3D for this member, let me show it bigger. Go to this other slide. Okay, so if we consider this part in here, now it is braced on the weak direction or the weak axis. So what is actually the strong axis and what is the weak axis? Let's take a look at this IPN 450, the top view for the wide flange. Now with the x-axis is considered as a strong axis, and the y-axis is considered as a weak axis. Why is that? Because if we go to the section tables and check, for instance, for any kind of IPN value, let's say IPN 450. For IPN 450, if you compare the moment of inertia about the x-axis and the moment of inertia about the y-axis, you will see that always the moment of inertia about the x-axis is bigger than the one about the y-axis. That's why the x-axis is considered as a strong axis and the y-axis is considered as a weak axis. But don't let this fool you. Someone might call this as x-axis, and this one might call this as a y-axis. So you have to understand by looking which one would be stronger. Also, as in the problem said, braced in the weak axis for the weak direction. So I have a pin support here, pin support there at the mid height and there. And when it comes about the strong axis, which is the x-axis, bending about it, I have just a pin from the top and the bottom. Now, if we understand this, we can solve the problem. So first of all, we have to check the slenderness. Now, since the case is pin here and there, and also in the weak direction, it is pin, pin, and pin here, the K value would be taken as 1. So if we check for the strong axis at the beginning for the strong axis, it would be only pin support from top and pin support from bottom. So in this case, K would be 1, and the length would be 3.6, the distance between these two supports. And Rx, you would obtain it from the sections table. So if you calculate this, you would obtain KL over Rx would be equal to 20.34. Now, if we check for the weak axis about the Y, now we have K is equal to 1 again, but this time, since I'm considering the Y-axis, which is the weak one, I have a support here. I have a support there at mid-height and another support over here at the bottom. So usually you have to consider actually both pieces. You have to consider this piece of the column and this piece of the column if the distances were different. But since the distances or the lengths, the lengths are the same, I can take whatever I want. So in this case, this is a pin, pin, pin. I take one of them, and the length would be 1.8. As you can see here, now it's 1.8 compared to 3.6 previously. And if you substitute for the value of Ry, you would get your KL over Ry equal to 52.48. Now, which value am I going to use to calculate the compressive strength? I will take the biggest one. Again, because of the plot that we have here. So after taking this value, I can check the slenderness. And if you do that, you will find out that KL over R is actually less than this value over here, which would be 127. Now, if we continue, because the value of KL over R is less than, I'm going to use FCR equal to 0.658. And before that, I have to find FE. So what's FE? Again, we substitute the values where KL over R now is equal to 52 squared, and FE would be equal to 716.7 megapascal. Now, if I proceed and calculate the capacity for this compressive member, or find FCR at the beginning, from this equation, you would get FCR equal to 234 megapascal. Now continue one more time with the capacity of the whole member by multiplying by the area gross of IPN 450. In case you don't know how to find the area gross of 450, I'm going to show you. You go to the sections table, you search for IPN 450, it's over here. And we look at the table. Here we have the area, this column, 147 centimeters square. Converted to meters, it becomes 14,700. Multiply by FCR, you obtain the capacity equal to 3,100 almost kilonewtons. Now, this is the capacity for this compressive member. Do you have any questions, guys, for this problem?
Hocam, can you explain again KL over RY part?
KL over RY part.
Yes.
Okay. So if we consider again, let's take a look again. Right, so for KL over RY, now K, when you have to consider it, first, since the column is divided into two pieces, I have two supports, one at top height and one at the middle height. And I have another piece where I have here a pin support and another pin support there. So if you check, for example, for this piece, it is pin from top and bottom. So for this case, K is equal to 1. What about the length? The length is equal to 1.8. What about R? It's going to buckle about the y-axis. So you will take RY for IPN 450, which would be equal to this value. Now, let's say that this part was not 1.8 meters, it was, let's say, 3 meters, for example. Again, you will check in here, you have a pin support, and at the bottom I have a pin support. So K is equal to 1. What about the length? Now the length would be equal to 3 meters if it was different length. And lastly R, Y, because again the section is buckling about the y-axis. And you will have the same RY value because the section did not change. Did I make it clear?
Yes, John, thank you so much.
You're welcome. Any more questions, guys? Okay, I'll move on to the next problem.
Yeah.
Yes.
Yes. After that, you will sum the both results, right? For 1.8 and 3 meters.
No, you don't send the results. No. Don't be careful. Don't do that. Wait a second. If this one was 3 meters, let me continue. You will have to check KL over RY for this part. So this becomes 1 for K multiplied by 3 meters divided by RY 3.43 divided by 100. Let me check and calculate. This would be 87.46. Now realize something. You have this value, you have another value there. You will treat each one differently. You will not sum anything. You will just consider this figure here, which is KL over R. This is your FCR capacity. So which value am I going to proceed with? Now, of course, the biggest value, which is this one, 87 now, because this would result in a lower capacity for the column. So you basically do not sum this value and that value. This is wrong. Is it clear?
Yes.
All right. Any more questions? Okay, let's go to the next problem. Now, in this problem number 3, it says, shown below is a portion of a multi-story unbraced frame. Now, notice something, it says unbraced frame. Every piece of this question is important to read. All stories are 3.5 meter high. All beams are IPN 380. You're given all the beams sections. Out of plane, all columns are braced top and bottom. So this is another piece of information we have. And it says KY is equal to 1. Design column AB. Column AB is over here. Design column AB. Choose the lightest I shape of S275. Assume the columns above and below are the same as AB that you will design. Given axial load was determined based on LRFD load combinations. You have to try sections IPN, IPE, HEE. I mean, it's a very long list. But anyway, so let me explain at the beginning, before we proceed with this question, what we see in front of us. In front of us, here we have the column AB. And what you see again here is actually in plane. So this is your N plane. Now, when it says to you out of plane, it means if you look from this direction, right there, you would see that all columns are braced top and bottom and given to you ky is equal to 1. So I expect something, if I look from this direction of arrow, I expect something like this. This is how AB would be. So differentiate between in plane is what you see in front of you, out of plane is what you don't see. Also, we have in here, we are given the direction of the column which is set, the wide flange. Now this is important to realize whether it's buckling about the x-axis or it's buckling about the y-axis. So this is important piece of information for us. And usually the beams are placed in such a way that they buckle about their strong axis. So this is how a beam would look like. This is a flange, and this is the wood. Now, after understanding all of these things, also we are given the load combination 5,000 kilonewtons. We have to design column AB. So in order to start with the design, I have to find the area gross minimum to pick a section from the sections table. And to reach this point, first I have to find the slenderness. So for the slenderness part, KL over R, I have to start with an assumption. So I'm going to assume that KL over Rx, Ry, it doesn't matter. In general, it's going to be 50. This is an assumption I have to start with. Then I have to check for the slenderness, whether KL over R is less than or bigger. And in this case, if you compare the 50, you realize that it is smaller. Therefore, you can calculate FCR equal to 0.658. Now, before that, I'm going to calculate FE. What's FE? I'm going to substitute with my assumed value of KL over R, and I will get FE 784 megapascal. Now I can go to FCR. I have everything I need. So FCR would be equal to 237.7 megapascal. Now, since I have FCR, and I'm given in the problem that the load is 5,000 kilonewtons, basically what I'm going to do is divide the load by the FCR. Now, of course, you still remember this equation. The capacity of the member is equal to 0.9 by FCR by AG. So if you manipulate this equation, this is what you would get. AG equals to Pn divided by FCR. So if you calculate this part, you would get AG equal to 0.021 meter square. Converted to centimeters, so you can look into the section tables, you would get 210 as a minimum area you need to start with. Now you can start searching in the section tables. So this is 210. I go and check, for example, beginning with any section I need. So we were given in the problem that we can check IPN, we can check from IPE, HEA, etc. So I'm going to directly check for IPN 600, and I get my AG bigger than what I need. RX, RY, and IX, these are some values I'm going to use. So continuing, first of all, we will consider the N plane. The N plane is what we see in front of us. So in that case, I have to find K value. Now, since it is connected by a beam in here and there, and I have a column at top and column at the bottom, I have to calculate something called G top and G bottom. So what is the G value? G value is equal to the summation of EI divided by the length of a column, and same divided by the length of a beam. Now, note something, when you consider the moment of inertia for this would be for a column, and for this one would be the moment of inertia for a beam. And we are considering 2 points now. A point over here, let me erase this. What I will find right now, G top, this point, and G bottom, this point. So at the beginning for G top, now if you take a look at this point at A, you will find that there are 2 columns connected to this point. This column AB and the column above it. That's why I have 2. Now multiplied by the moment of inertia of each column. Now notice that in plane they would buckle about the x-axis. So in that case, I'm taking IX for IPN 600. I substitute it in here and divide by the length of the column, 3.5 meters. Now I have to consider for the beam. Now again, if we go to point A, we have a beam connected in here, another beam connected there. So 2 beams are connected to this point. That's why I have 2 multiplied by the moment of inertia for this section of these beams, 240, divided by 10, the length of a beam, 10 meters. Now in this case, you would get G top equal to 16.54. Let's check for G bottom. Now for G bottom, I'm going to consider point B. If you take a look at point B again, I have a column AB connected to it, and the column below it, which is the same IPN 600. So that's why I have 2 multiplied by moment of inertia again, divided by the length of a column, and the same as we did before on the beams. How many beams are connected? 1, 2, and the moment of inertia for each one of them, since they are bending about the strong axis. So I take IX for a beam, and lastly divide by the length of the beam. Now I see here that G top and G bottom are both the same. Now, because of this, since I have now G top and G bottom, I have to consider whether the end plane is braced or unbraced. Why? In order to actually find the K value. So if you remember from the problem, now the problem says, the problem says that shown below is a portion of multi-story unbraced frame. So it says here it's unbraced frame, while the out of plane is braced. Now in this case, if I go to AIC, I can find my K value from one of the graphs. So where do you find these graphs? We go to AIC and check. You have in here at page 55 and 56 2 figures. So first one, we have the alignment chart where the frame that you have is braced, and we have the other one for the case which is unbraced. Side sway is uninhibited, so that means that it can sway around. So since it is unbraced for the end plane, I'm going to use this one. By the way, guys, we have less than 10 minutes. If this one disconnects, please connect again. Now, I took this from AIC. I check for G top and G bottom. So as we said, G top is 16.54. It would be somewhere around here. And G bottom is 16 again, somewhere around here. Connect these 2 points by a line, and you would get your K value. So this is my K value now. K value would be equal to 3.6 approximately. Now I can proceed and check in plane and out plane, KL over Rx and KL over Ry. for the column that I'm designing. Now, if you check for the end plane, 3.6 is the K value, 3.5 is the length of the column, and I have Rx, since it would buckle about the x-axis in the end plane. And you would get your KL over Rx value equal to 53.85. Now, if you check out plane, now in this case, I have K is equal to 1, since the problem says that in the out of plane, it is pin, or it's given to us actually Ky equal to 1, multiplied by the length 3.5 divided by Ry, since the buckling now out of plane would be about the y-axis, which is the weak axis. And you would get another value for KL over R, 81.4. So which one am I going to use? I'm going to use this one, since it is more critical. Now I proceed and calculate FE. FE is going to be pi square multiplied by the modulus of elasticity divided by the biggest KL over R value, which is this one. And from there, I get my FE 297 megapascal. Now I can check for FCR. FCR is decided from the slenderness. Check the slenderness. 81 is less than or equal to 127. So for this case, I'm going to use this equation. And if you check FCR, you would get 186.87 megapascal. Check for the capacity of this member, IPN 600. And you would get the capacity for this member is 4,271, which is less than 5,000 kilonewtons, which is less than what we need. So this is not good. You have to check another section. So now I'm going to check HEB 500. Ignore this, please. If you take all the information that you need again, as we did before, and check for the end plane again, check for the G top and G bottom again, because the moment of inertia for the column has changed since it is a different section. So if you consider G top just the same as we did before, the only value will change here is the moment of inertia. The beams are the same, the length is the same, but the moment of inertia changed. So I get my G top equal to 12.76, and same for G bottom. Now in here I have these two values. I'm going back again to my chart, alignment chart, where the side sway is uninhibited. So in here I connect these 2 points, 12.76 and 12.76 in here, and I get my K equal to approximately 3.2. Someone might say, how am I supposed to find this value? Here you have a 3, here you have 4, and here is 3.5. So it's approximately 3.2, 3.3, it's fine. Now we check again. This is the length. This is my new Rx value from the section table. I check, I get my KL over R 52.9. Now I check for the out plane. My K value is now equal to 1 multiplied by the length divided by Ry, 72. And I get my KL over R equal to 48.14. Now, as you can see here, which one is more critical? This one. Now, the end plane is critical in this case. So I can proceed now and check for FE. Calculating FE based on this KL over R value, 52.85, you would get 706 megapascal. Now check the slenderness. 52.9 is less than 127. So you will be using this equation. And if you use this equation, you would get FCR equal to 233 megapascal. Now continue one more step. Find the capacity by multiplying by 0.9 by the area gross for HEB 500 and FCR. You would get your capacity equal to 5,017 kilonewtons, which is bigger than 5,000 kilonewton. This is something good. So you can stop right here. Now, in case that you were actually going to literally try every single section as the question asks, Now in the question, as we can see here, it says try IPN, IPE, many sections. So if you literally try that and you found that many sections actually suit you, which one are you supposed to check? Give me a second. So about question number 3, yeah. So in here we can see that they checked many sections. And we see that, for example, this one is okay, in plane, out plane is okay, in plane is okay, out plane is okay. So many sections actually fit. But which one is the one that they pick or you pick is the one that is lightest. So first of all, you have to check whether it's safe. You check it's safe. And after that, you decide which section am I going to take. You take the lightest section since it's going to save you a lot of money. How do you decide that? You go, for example, to section tables. You compare, let's say, IPN 450 with IPN 400. Both of them satisfy the safety, but you check for the weight. Now, the weight for this one is 92 kilograms per meter, and this one is 115 kilograms per meter. Since both of them satisfy the safety, I will pick IPN 400 since it is the lightest, cheapest. So that's how you solve this problem. Do you have any questions, guys?
I have a question, Hocam.
Yes.
For the beams, how do we know that it will buckle around the strong axis? In the question, it didn't show the illustration or position.
Let me see. Well, usually, I mean, like always, we set the beams in a way that they would buckle about the x-axis. But in this problem, yeah, as you say, it did not mention. So in any case, this is something you can like always know. The beams are set in a way that they would buckle about their x-axis or rotate or bend about the x-axis. Because of course, since the load would be vertical on them, we need the strongest axis to resist the loads. We won't put the weakest axis facing the loads. So this is something to know. Beams are usually bending about the x-axis unless it says that it's bending about the y-axis or the weakest axis, etc. Now in this problem, you were supposed actually to be given sort of like a drawing like this one for the beam, but it's not given. Maybe I can see another example. Yeah, so for example here it shows you for the beams. For the beams, these ones would buckle about the x-axis. This is a section showing you a section for the beam. So as I said, usually they buckle about the x-axis. Now we have less than a minute. I have to close this one, open another one. You can continue asking after I initiate the other one. Okay, now, oh yeah. Do you have any questions, guys, about the previous problem that we did?
Hocam, why did we check for both out and in plane?
Because you don't know actually where the column is going to buckle about. Like, it might buckle in plane. In plane might be buckling like this. Or the out plane would be buckle again. If you take a look at the out plane from this direction, there is a risk of also buckling. If it was pin, for example, from the out plane. So usually, like in the solution, what they did is that they calculate for in plane and out plane. But I took a shortcut, which is something you can do because of this plot that we know, KL over R. As KL over R increases, the FCR decreases, which means the capacity decreases. So based on this, I can reduce my solution and I can know which plane actually would fail, which one is the riskiest, let's say. Did I answer your question?
Hocam, but we already checked slenderness. Isn't it enough?
That's the slenderness part. That's not enough.
That's not enough, right?
No, that's something you do in order to decide which equation for FCR you will do. Either 0.658, or you will be using 0.877 by FE if KL over R was bigger. But I mean, this one is mainly what we are focusing on. This is the step before the slenderness. Now, in order to be like 100% sure about your solution, it's better to actually check in plane and out plane. What do you mean? What do I mean by that? So for example, in here, I picked the biggest value. Now what you can do is actually proceed with both values. You can check for 52.9 and 48.14. How do you do that? You will check for FE. You will have FE, this one, and you will have another FE for the out plane, where you will have KL over R is equal to 48. Now after that, since you have two FE values, you will check the slenderness. Check the slenderness for in plane, check slenderness for out plane. Then proceed, you will have FCR here and FCR for out plane. And you will see like by yourself like two capacity values for in plane and out plane. And of course, the lowest capacity value is your limit. Any more questions?
I have a question. At the beginning, when we're assuming a value of K over KL over R,
Yes.
if you, for example, choose a bigger value than the K limit, and we have an elastic section, for example, does this change the results?
Of course, look, actually, at the beginning of your assumption, I'm not sure like how high you would pick, like maybe 1,000. I don't know what would happen if you choose something really high. But if you choose something between maybe 50 and 120 or so, or even above 127, it's fine. You're starting with an assumption. So let's say maybe you can have a range for KL over R assumption, where it is maybe between 150 and 50. There isn't like such a rule. You're starting with an assumption to figure out a section. But usually the best values to pick is like 50, 60. These are the best assumptions, I would say. Because let's say that you assume a very high value for KL over R. You might get AG equal to, instead of 210, you might get 100. What does that mean? It means that you have to go through many sections. So we are picking a point which is almost in the middle. I pick a 50. Maybe you can take a 60. Something like that. Is it clear? Hello? Any more questions, guys?
Udam, I have one question.
Yes.
Related to bracings. Like, what happens is, when it's like not in the middle? For example, like if it's like 4 meters length, would there be any situation like 1 and 3 meters?
I didn't understand your question. Could you say it again, please?
Like, for example, in the bracings,
Yeah.
they always put it in the middle, but if there is there like any case that they don't put it in the middle?
I think we will see a case where it's not in the middle.
Okay. Thanks.
No problem. Okay, let me go to the other problem now. I'm skipping problem number 4. I'll go to problem number 5 now. In this problem, it says for the box column shown below, determine the value of A. This is the value of A for you to find. such that the column can safely carry a load of 1,750 kilonewton, which is determined using ASD, load combinations. Use recommended K values, and you're given the steel, which is steel, is 275. So as you can see here, I have this section. The white part is a hollow, so it is a box plate, and we are given the load according to ASD. I have a fixed support at the bottom. Now from this information, I can find my K value. Now for this problem, how do we solve it? First of all, I have to set my equations as if I'm calculating everything fine, but with a variable of A. Again, ignore this for the meantime. So let's take a look at here. Now, if you calculate the area gross for this section with my variable A, which I'm interested in finding, it would be A square, the whole square, minus the square inside, which is the hollow. So this is how I find my A gross. Now, if we continue, simplify the equation, it would become 60A minus 900. Now I have an equation for AG. Now I will continue and find the moment of inertia. If you consider the moment of inertia about the x-axis or the y-axis, both of them would be the same, since it is symmetrical shape. So calculating moment of inertia would be, in here I calculate it in this way, this square minus the inner square. That's why I have 1/12 by a to the power of 4 minus this value. Organize the equation and find the radius of gyration. So the radius of gyration is actually equal to square root of moment of inertia divided by AG. Now if this was Rx, this would be Ix, and if you're finding Ry, this would be Iy divided by AG and the square root. Now, if you put everything you have found, AG and I, in your equation, your radius of gyration would become like this. Now, here's this part. Now, we have all the equations that we need, or let's say if everything I need in a variable A, I have to start checking some values for finding the optimum value for A, which is my variable. So what am I going to do? I start with an assumption again. I will assume a value for A, which is equal to 100 millimeters. Now, if you do that and calculate R from this equation, you will put the value 100 here and there. You would get your R equal to 35.23 millimeters. Now check for KL over R. Since it is bending about, both directions, it doesn't matter Rx, Ry. And for the case where we have a fixed base in here, the K value would be equal to 2.1 multiplied by the length, 6,000 millimeters, divided by 35.23, which is my R value I just found. So KL over R now is 357. That's a very high value, more than 127. So I'm expecting a very low capacity for this member. Why? Because of my famous plot I have in here, KL over R and XCR. So if I continue now and check for FE, my FE would be equal to pi square multiplied by the modulus of elasticity divided by the KL over R value I just found. My FE now is 15 megapascal. Now I can check for FCR. Of course, you have to check the slenderness. This is where I check it. That's why I'm using FCR 0.877 multiplied by FE. Now from here, your FCR would be equal to, give me a second, let me clear things. So now, since I have FCR, it would be equal to actually 13.153 multiplied by, sorry, let me check. So it seems like there is a missing part for this. Let me tell you. Ignore this part and let me, sorry about this, let me calculate this part. It's missing. This is actually equal to 13.53. You will take this value and multiply it by the gross area, 13.53, multiplied by the gross area in here. If you calculate it based on your assumed value 160 by 100 minus 900, oh yeah, it's actually going to give you 5,100. And divide by the ASD factor 1.67. So this was correct actually. You would get your capacity based on your assumption equal to 41 kilonewton. So this part actually was correct. This is the area in here, and I have here FCR, and this is based on ASD. Now 41 kilonewton capacity is lower than 1,750. So I have to increase my value for A. Now, if we check another value for A, now we assume, for example, 330 millimeters and calculate again R based on our equation we found previously. You get 128 millimeters. Check for KL over R, 2.1, 6,000 the length divided by R. Now 97 is less than 127. So that decides which FCR equation that you're using. Continue and calculate FE. Substitute by, okay, this is a mistake in here. This should be 97.87, the KL over R value. Square that and calculate FE, you get 206 megapascal. One more step, FCR. Plug in all the values that you have found and your FCR would be 157 megapascal. Now check for the capacity of this member, 157 for FCR, and area gross based on the equation previously we found for area, divided by ASD, 1.67. Now the capacity of this member is 1,780 kilonewtons, which is slightly bigger than 1,750 kilonewtons. That's good, and you can stop here and choose A equal to 330 millimeters as an optimum value. Now this question actually requires lots of iterations, and usually it's better to do it using computer, because if you will keep using many values, you will take forever to actually find the optimum one. But I show it in here so you can have an idea. Now, do you have any questions before we proceed? Okay, no one has any question. Now moving on to problem number 6. In the problem it says all columns HEB 650 and all beams HEA 500. So we're given the sections for the columns and for the beams. And it says that strong axis bending for the beams. So if you take a look at the orientation of the section that you have for the beam, the buckling for the beams would be about the x-axis or the strong axis. Now it says also out of plane, all columns are supported at story levels. Use K equal to 1 for out of plane. Now what you see in front of you is in plane. For the out plane is when you look from this direction. So this is out of plane, this is what you can't see. You take it, you take K value equal to 1. Also it says all members are S275 steel. We are given that Fy is equal to 275 megapascal, and we are supposed to calculate design compressive strength and allowable compressive strength according to C for columns A, B, C, and D according to AIC specification. All beam to column connections are rigid except for one. So all the beams connections to columns are rigid except for one, which is shown over here. This one is pinned. And we have to use recommended G factors for column bases. So looking at the problem, this is the frame we have. We're given all the dimensions for this frame. We're given the orientation for the columns. Those orientations we have here are very important, so we can understand the buckling about which axis. And we are given the information about the sections for the beams, the columns, and we can start solving the problem. So first of all, in order to find the capacity for column A, I have to find the G values. Find the G values in order to find K value. And in order to calculate the G value, first of all, I have to consider the in-plane part, calculating the K value in the in-plane. I will consider the G values to calculate that K. And first of all, we have this equation, as was shown before. Based on this equation, I will find the G values. So for column A, I have to calculate G top, which is the point shown over here. At the G top, I have to start substituting. I'm looking at the G top. How many columns do I have connected to that point? I have only one column connected to it. Therefore, 1 multiplied by 139.8 e to the power of 6. And that 139.8 is actually which I? It would be IY. Now, how did I know that? Because the column is going to buckle about the y-axis, and therefore I substitute IY for the HEB 650, which is the section of the column. And I divide by 3.5 because of the length of the column. Now I consider the beams. So for the beams at this point again, the G top, I have 2 beams connected to it. And those beams have IX, they are bending about the x-axis, the strong axis. Therefore, I take the moment of inertia IX, and I divide by 8 because of the length. Now, we consider the G-bot. For the G-bot, I have this point for column A again. Now, at this point, as you can see, I have the column, the upper column that is connected A, and the bottom column connected to it B. So I have 2 columns. Therefore, I substitute the value 2 in here, multiplied by IY, and divided by 3.5. Now, if we consider the capacity for column A at the beginning, I have to calculate the value of K for the in plane and for the out plane. The out plane is already given to me. So in order to find the K value for the in plane, I have to calculate G values. So for column A, again, I'm checking in the in plane, and I will be using this equation for finding the G values. So if I check for the value for G top, here I have this point, I call it G top. I will calculate it now. So looking for the part about the columns, how many columns do I have connected to this point? I have just 1 column, and this column has a moment of inertia equal to 139.8. Now notice something, this I value, or the moment of inertia, is actually IY. Now why is that? Because the column would be buckling about the y-axis when we are considering the in-plane. Therefore, I substitute the value of IY. Now, if we consider the part for the beams, again, we are looking at the point over here. I have 2 beams connected to this point, and therefore, I say 2 multiplied by the moment of inertia about the strong axis, because the beams are oriented in such a way that they would buckle about the strong axis. So here I have the IX for the beams. Now notice also I divided the columns by 3.5 because their length is 3.5 meters, and the length for the beams is actually 8 meters. Now I have to consider also the G bottom, but first let me erase. Okay. Now, if we consider the G bottom, I'm at this point right now. Again, for column A, I have at the G bottom, I have now two columns connected to this point. I have column A and column B. And therefore, I say 2 multiplied by the moment of inertia Iy again, because they would buckle about, or the columns that they are connected to this point would buckle about the weak axis, y-axis. And I divide by 3.5 because each one of them have a length of 3.5 meters. And then when I consider the beams, again, I have 2 beams connected to this point. But notice that this time, there is a beam that has its far end is pinned. So because of this reason, first I'm considering this beam over here. I say 1 multiplied by the moment of inertia Ix for the beam divided by 8, its length, and then plus 0.5 because of the far end is pinned for that beam over here. So 0.5 multiplied by Ix divided by 8. Now, regarding this value, if you go to AISC, and okay, before that, I have to mention something. So if we consider this floor where the column A is located at, we notice that there is no bracing. And if you apply a horizontal force in this direction, this floor would sway with respect to other floors. And therefore, because of no bracing, there would be sway. So if we go and check for the AISC again, and it says for side sway uninhibited, you have to take the value if the far end of the girder is bent, multiply EI value by 0.5. So based on that, I chose the value 0.5. Now, after calculating G top and G bottom values, here we have the explanation. So this is actually far end bend and side sway is unprevented, is not prevented. Now this floor, as I said, the side sway is not prevented where the column A is located. When we look at the column B at this floor, we see that there is a bracing. And because of this bracing, the side sway is prevented. And also same applies for this floor at the ground level. We see that the side sway is prevented even though that we have one bracing on one bay. It would give the effect for all the floor. All right. Now, after that, I can calculate the values actually for the K. So for the end plane, again, I'm talking about the end plane, and I consider the G top value and I found the G bottom value. So I go to the alignment chart that is available in the AISC as well. And as we said before, side sway is not prevented. Therefore, I go to the associated alignment chart and I plug in the values for the G top and G bottom. So for instance, I have here plugged in the value for G bottom, and here is the value for G top. Connect those points with a line, and from the middle line, you can calculate the K value. Now it appears that the K value is equal to approximately 1.1. So I substitute in my equation KL over R 1.1. 1.1 multiplied by 3.5, that's the length of the column, and divided by Ry. Now, why did I choose Ry? Because again, the buckling would be about the y-axis for this column, and divided by 1000 for converging. Now from here, for the end plane, KL over R is equal to 55.08. Now I check for the out of plane as well. Now for the out plane, it is given to me in the problem that K value is equal to 1. Again, I multiply by 3.5 and I divide by 271. Now this 271 value is actually Rx, because in the out plane, the column would be buckling about the x-axis. And from here, you get the value for the outplane KL over R equal to 12.9. Now, which one am I going to proceed with? I will proceed with the biggest value because of the graph we all know. As the KL over R value increases, the capacity of the member decreases. Based on that, I carry on with the 55.08. But first, I calculate FE now. FE is equal to pi square multiplied by the modulus of elasticity for the steel and divided by KL over R squared. Now, from here, FE appears to be 650.64 megapascal. After that, we carry on and check for the slenderness. So for the KL over R value, it is 55.08. We check if it's bigger than or less than 4.71 multiplied by square root of E divided by Fy. And based on that, it seems that the KL over R value is less than 127.09. Now from here, I choose this equation. FCR is equal to 0.658 to the power of Fy divided by Fe and multiplied by Fy. Now, if you calculate this, it appears that FCR is equal to 230.41 megapascal. Multiply it by the gross area for the column. This is A gross for HEB 650, which is the column. And this is FCR. And we multiply by 0.9 if we are calculating in accordance with LR of D. So from here, the capacity of column A appears to be 5,937 kilonewtons. Now, coming to column B, checking its capacity, again, we check for the G values. In plane, we start with in plane based on this equation. So first of all, we have the G top. All right, sorry about this. Okay, so for the G top value, I'm calculating it now. G top for column B is this one. Now, if this floor was unbraced, the G top value for column B, G top value for column B would be equal to G bottom for column A. But since the side sway is not prevented for column A and prevented for column B, I have to calculate it again. So this does not apply. Therefore, G top for column B, I have two columns connected to this point, A and B, 2 multiplied by IY, because the column would buckle about the weak axis, and divided by the length of each column, 3.5 meters. Now, considering the beams, first I have this beam, 1 multiplied by Ix divided by 8 for the beam, plus, again, Ix divided by Ix for the beam, divided by the length, but this time, notice I multiplied by 1.5. Previously, I multiplied by 0.5 for A, but for column B, I'm multiplying by 1.5 because at this column, I have the side sway prevented. And if you again go to AIC and check, so it says if the side sway is inhibited, we take the value to be 1.5. If the far end of the girder is bent, multiply EI divided by L of the member by 1.5. And it says here for side sway inhibited, which means prevented. Okay, now I calculate the G top value for column B. It appears to be 0.292. And I check for the G bottom as well, again for column B. So this is G bottom. Again, at this point, I have two columns connected to it. Therefore, 2 multiplied by IY for the column divided by 3.5. And then I divide by, or if we consider the beams, now it becomes 2 multiplied by 869.7 divided by 8. So notice I multiply by 2 because those beams, this one and that one, they don't have a far end bend or any other conditions. They have rigid connection with other columns. Therefore, G bottom appears to be 0.367. Now, if we go to the alignment chart, but notice alignment chart of side sway inhibited, and plug in the values for G top and G bottom, you get your K value. Now, K value is approximately equal to 0.64. So when you substitute for the KL over R value for the N plane, since you found K value for the N plane equal to 0.64, I'm checking the N plane first, multiply it with the length of the column and divide by RY again, and divide by 1,000 for conversion, you get your KL over R with N plane to be 32.06. Now, if we check for the out of plane, so we were given also K equal to 1, multiplied by 3.5 the length, and divided by 271. That's Rx, because in the out of plane, the column would be buckling about the x-axis again. And again, divide by 1,000 for conversion. And that would be equal to KL over R out of plane would be equal to 12.9. Now I have two values. Which one am I going to proceed with? I'll proceed with the biggest value. Now I calculate the value of FE. Sorry, for the FE, sorry again. So for the FE, it is equal to pi square multiplied by E. And we divide by the biggest value of KL over R, 32.06 squared. Now from here, FE is equal to 1920.18 megapascal. And here we have a late explanation. Far end bend and side sway is prevented for the 1.5. Okay, now going back again, so we were at FE. We found FE, we check for the slenderness. Again, it appears that KL over R is this time this value of 127. Now I check for the FCR based on this equation. This is FE, the 1920, and this is FY. And everything would be equal to 259 megapascal. That's FCR. Calculating the capacity of the member. So FCR multiplied by A gross for HEB 650 and multiplied by 0.9 according to LRFD. And you get the capacity of column B to be equal to 6,674 kilonewtons.